Okay, I run the tool again, still not working, and we will summarize for chapter 9, and we will have to see what was the issue there. Okay, now what we're gonna do is that we will skip chapter 10 for now. We will work on some decision analysis, and then we will back on chapter 10. Okay, but before we move on that, we will go over some of the chapter key issues. This part was that we do network analysis for transportation and a lot of things, approximately analysis, data mining. Proximate buffers, we did buffer, point line and polygon buffers, and poverty study statistics. For example, here we have the mean percentage for total population living in poverty within 2 miles of 2 polluting companies. That is 23.25% for those living outside of 2 miles of 2 top polluting companies. The mean percentage of poverty is 9.54. And then the green space near schools that you can calculate how much acres is there and access to work study polygon buffer created around PAT bus routes. This is really nice, okay? And then multi-ring buffers, which is really nice as well. Obesity patient near parks, wow. That we could see patients with moderate BMI decrease 43%, 75% live with 1,200 feet of a park. Patients with moderate BMI increase 83.3% live farther than 1,200 feet from a park. And pedestrian accidents near the parks. So injury rate per 10,000 youth in 37% higher in the 601 to 1200 feet buffering of parks compared to the 0 to 600 feet buffering. This is really interesting as well. And also we have to the example here, drug-free area near school, youth living near swimming pool that slated to close. And networks, the networks we did was use street central line and distance or travel time instead of buffers. And we create the service area gravity model to determine whether a random sample of youth owning pool tags, which allow admissions to pool falls off as they live further away from pools. Service area in minutes, and then we have a total example, the facility location. We have network location, a location model to choose the best system of 32 pools to keep open using geographic access criteria. Transportation networks, the street centralized layer, not self-aware of connectivity or turn constraints. Network data sets elements, address are the street and other segments over which we travel. Terms, the features that describe connections between address junctions, points that which different kinds of network connects. So metro station, bus station, railroad station. Okay, the data set, Tiger Street Central does not include one-way street or turn restrictions at intersections. Only uses typical travel speeds for road types instead of actual travel speeds. Only uses typical time delays for moving through or turning at intersections. And the street central lines classified by street type, the Tiger class code, and the data mining cluster analysis, which we had the problem. A bunch of studies that we went through. So we went through the branch of data mining. The goal is to find hidden structure in large and complex data sets that has some interest or value. Exploratory method, no right or wrong cluster. And the tutorial that we went through, we talk about the k-mean clustering. It's a heuristic algorithm, partitions a dataset with n observations with P variables into K clusters. Crime data set with N equals 303 observations will equals 4 variables for clustering, crime hierarchy, gender, race, and age of arrested actor, and K5 clusters. And we didn't get this result. We didn't get any results for this. It should be interesting to see. For some reason, the toolage is not running, and we do not have any PDF that got generated. I think something is missing here. And we copy Python command and see what's going on. We could do that, and we can just paste it here and there. So alright, so we could do is import ArcPy, and then so that was the issue, and I still don't understand what's going on. And we can change some parameters here. So serious violent crimes, yeah, and we match, and the CNN is here. Serious violent grouping, yep. We can change that. Hierarchy, we choose hierarchy, arrange gender, arrange race. And then arrange standard deviation, no spatial constraint, Euclidean, none, and none, get seed from field, and then we have a seed, and we have our PDF report. Do not evaluate things. So everything looks perfect, and I don't know what was the issue here. And we follow everything. So grouping analysis, statistics. So maybe we will change it. Grouping analysis? I don't think so. Okay, statistics. Okay, so I could recall ArcPy statistic grouping analysis. Instead of that, I could say, where did the tab go? Oh, right here. Grouping analysis statistics. Okay. I could just change it real quick. Okay. I would say import ArcPy, and then grouping statistic analysis, and underscore statistic underscore, and then we hit enter. Yeah, failed to execute it. We have to see what was the problem, and I might have to contact the team to say what's going on for the grouping analysis. All right, I'm gonna save the code. Okay, so now we're going to move on. We do not have anything, so here I'm gonna use is the using ArcGIS Pro workbook, that we will go to hurricane damage decision. So to talk about that, we could just learn a little bit. Let me get back here. That we will do is hurricane damage decision. So talk about in 2005, Hurricane Katrina, Rita and Wilma destroy homes. So if we want to learn more about it, so and in business, infrastructure, and natural resources along the Gulf of Mexico and Atlantic coasts. So in the aftermath of the storms, federal, state, and local governments, service agencies, and the private sector responded by helping rebuild the hurricane ravaged area and restored. Monitor the local economy. And we also, the local economies. So GIS helped corresponders assess damage, monitor the weather, coordinate relief efforts, and track health hazards, among other critical tasks, by providing relevant and readily available data. Maps and images. In this module, we will access some of the same data that guided critical decisions such as funding and safety measurements in the wake of Hurricane Katrina and Alma. We will map elevations and bathymetry, animate the hurricane's path and changes in pressure, analyze flooded areas and storm surges, and pinpoint vulnerable infrastructure in the real world. This analysis saves time, money, and most importantly, lives. So what we have to do is we will build some skills, classify and symbolize the data, use time-enabled data, perform geoprocessing, use raster calculator, summarize statistic, use ArcGIS spatial analysis extension, and create and publish a crowdsourcing map to report storm damage. That publisher or administrator organization, we need ArcGIS Pro. So here we learned that on Monday, August 29th, 2005 hurricane. So Hurricane Katrina hit the Gulf Coast of the United States, devastating the wetlands and barrier islands. So 3 counties in Mississippi there hit partially hard. To access and remediate the damage caused by the 15-foot storm surge that hit the coast, the team of GIS specialists must prepare maps and calculate damage. The information will help federal officials decide how to allocate redevelopment resources. So in the aftermath of the hurricane of 2005, considerable thought has been given to better preparing for such disasters. For more insight, refer to the paper. Of course, there are a lot of paper talk about it. And the Gulf Coast contains much more of the nation's most fragile coast ecosystems. Barrier lands, coastal wetlands, and forest wetlands all play a critical role in the environment. The barrier islands prevent storm surge and saltwater intrusion, and coastal wetlands provide habitat for mammals and waterfowl, while also serving as a nursery for the Gulf fishing industry. Forest wetlands provide a renewable resource for the paper and timber industry. So the problem is, federal officials must decide where to allocate disaster aid to the Mississippi counties most affected by Hurricane Katrina. We will assess the total acreage for different types of land cover that were underwater as a result of the Katrina storm surge. The damage reflects the unique hydrography of the Gulf Coast. So we must map that as well. We will map damage to the infrastructure and healthcare centers so that restoration efforts can focus on areas with the greatest need. Our team must prioritize locations for disaster aid justified by the data provided and the maps and types we produce. A crowdsourcing map will be produced so that the general public can report damage. So deliverable. We will talk about the deliverable. After identifying the problem we will try to solve, we must envision the kinds of data display maps and tables that will address this problem. We recommend the following deliverable for this. Here is a map showing elevation bathymetry, Mississippi coast counties with places, types of water, barrier land, islands, and rivers. This map should be also include a time series showing Katrina's track, a map of flooded land on the Mississippi coast after Katrina. The map would include a table showing percentages of total flooded land and acreage by land cover type, a map showing infrastructure and health facilities at risk from the storm surge, a published crowdsourcing map to report storm damage. And the question here